So I will just start by explanation the title. So if you have questions, just let me know because I'm using iPad, so it's very easy to write something. So it's about mean field limit problem. So what really mean field limit means, right? So maybe I stopped the video because I'm looking at the yeah. Okay. So if you have questions, just ask me, and I can just write on the iPad. Okay. So what a mean field limit means, right? It basically means we're starting from a microscopic system, which can be given by a ODE system or SD system. And we want to pass to the limit as n goes to infinity. So as n goes to infinity, we can recover, at least intuitively or not formally, we can recover a macroscopic system. Okay, so there's one case like for this larger n limit, it's called mean field limit. I will give you a concrete example shortly later. So quantitative methods, basically here I will present two methods. So one is relative entropy. So this is the first. Another one is modulated free energy. So use this method, we can quantitatively control the distance between microscopic system and macroscopic system. Okay, so you will see more details later. Okay, so those are joint work with Pierre Emmanuel and also recently with Didier Bresch. Okay. So before we start, let's just mention this, right? So this is the problem we are considering, mean field limit, right? It's one type of the large n limit problem. So actually there's a lot of problems in this flavor. It's part of Hilbert's sixth problem. So it's basically from atomic description, and you send n goes to infinity, the number of particles goes to infinity, you kind of get some continuous continuum description, right? For instance, given by fluids equation, nonlinear Schrodinger equation, like aggregation diffusion equation, etc. Right? The very first idea actually due to these two guys, right? This Maxwell and Boltzmann, in 19th century. So at that time, the atomic point of view of matter, right, are not very popular. So so actually, it's a very big idea, right? You just assume like the gas are composed by atoms, and you try to derive a macroscopic law, like Boltzmann equation, like from those particle models, right? So it's first appear in the study of now called Boltzmann equation. Okay, so like you can formally understand those problems, at least in this restricted setting, as deriving some macroscopic equation, right? So, but there are also other type, right, in this flavor. For instance, like hydrodynamic limit, BEC, right? Both are Einstein condensation, thermodynamic limit, and etc. Right? So this is the general type problems, and in probability, I think it's there are a lot of problems in this flavor called scaling limit. Okay, let's change your color. So so I'm starting from like kinetic theory. So in kinetic theory, this problem arises from the following specific problem you can see now. So we consider Newton dynamics. So this is Newton dynamics. So this is classical Newton dynamics, and xi is just the position. Vi is just the velocity, right? What we are writing here, right, is just Newton's law. Newton's second law for motion, right? So the acceleration is given by interaction force, right? So K is the two-body force. Two-body force. Okay, so we have n particles, and so you can formally think this as mass, but actually it's not. But you can think this is as the mass of each individual, each particle is 1 over n. The interaction from one individual is in the order of 1 over n, so which can be negligible, right? And we call this scaling the mean field scaling. So this is a mean field scaling. So formally, right? Formally, if we send the number of particles goes to infinity of this Newton dynamics, so we can recover one very well-known type kinetic PDE, right? So this is a Vlasov type PDE. So in particular, right, if we choose this K as the gravitational or Coulomb force, right? So which is just given by inverse law, inverse square law, right? Gravitational force or Coulomb force. So this equation, this PDE is called a Vlasov-Person. Okay, it's the macroscopic kinetic. It's actually it's a mesoscopic kinetic equation which describes the evolution of large scales, um, um, large scales astronomy models, right? Or some plasma physics models describing the evolution of ions in plasmas. Okay, so formally, right? So what we know, right? So classical result is okay. So if we know this interaction force is Lipschitz. So actually, if you send n goes to infinity, from particle system to the kinetic equation, this is known, right? So this is known, but for K is singular, right? For this interaction force is singular, people don't know, there are not many results, right? So I just mentioned several results, right? So this, so for this result, you can treat single kernels, which behaves like this, right? You have singularity, but the singularity is very, very weak. And so this result is you do some modification, right? We have a kernel which is singular, so we modify this, right? Basically, you can modify this by a smooth function, right? By smooth function, and also so this result is so we can treat a kernel, right? So which is bounded, but we don't need assumptions on the derivative, right? So recently, like Serfaty and with Durings, so they can treat not this Euler, not this Vlasov-Person system, but an Euler-Person system. So which is not this equation. This is not this equation, but actually the equation which is monokinetic. So if I give you a position x, right, and then a position, so the velocity is determined by this position. So it's called a monokinetic. It's actually Euler-Person system. You can derive Euler-Person system from particle models. But people still don't know, right? So this is still wide open problem. In the following, talk about this second order system, like from Newton dynamics to this. Instead, I will study the first order system. It's slightly easier, but it still capture the difficult part, which K is smooth, is singular, right? K is singular. Okay, so this is our setting. So now we consider interacting particle system. In the following, I will just write IPS, right? IPS, interacting particle system. So for simplicity, you can just think of those particles on torus, but this really doesn't matter. So we will do some technical treatment. Okay. So this is our particle system, right? So instead of the previous Newton dynamics, right? So this is velocity. This term is velocity. So velocity is directly given by interaction force. is directly given by interaction force, right? Instead of acceleration, it's given by interaction. So now velocity given by interaction force is a first order system, right? So again, we can consider the Brownian motion part, right? We can add noise. So this becomes a SD system. Again, right? So this is mean field scaling, and this is two-body force, two-body force. So we are interested in the case. So we are interested in the case K is singular. So when I say K is singular, right, basically it means the following, but it has other meanings. But let's just focus, for instance, this case. So Kx blows up. So if you send x to 0, this basically means, right, if two particles becoming closer and closer, right, so the interaction becomes stronger and stronger. Okay. So again, so this, so if we send n goes to infinity, we can recover those mean field dynamics. This is called mean field dynamics. So formally, you can think in this way, right? So mu n is the empirical mirror. So we just sum up all the Dirac. So this is a random. So this is a random mirror, right? So let's write it in this way. So this means a random mirror. So this mirror, right? If you send the number of particles goes to infinity, right? If you send n goes to infinity, so we can recover a deterministic mirror. So the goal of this talk is like to rigorously justify this, but in a different framework. But you can think in this way. So this empirical mirror converges to rho t, and rho t just to solve this mean field dynamics. So this is this from convergence from IPS, the interacting particle system, to mean field dynamics. So this is called mean field limit. So our goal is just to show this convergence, right? Just to show this convergence, and also quantify the
question.
Go ahead. Questions?
Yeah, so this empirical measure is random. So like it converges to this rho in what sense?
Yeah, that's a good question, right? So let me rewrite this. This kind of cheating, right? So what's this, right? This actually is a Dirac of rho t. So then this is also you can think this is Dirac in the probability space, right? So this convergence is converging in law. Okay. So you have a test function, right? You can have a test function phi, and you do the integral. And now you get a random variable, right? So phi is a test function. So then this converges to phi delta rho t. So it means this. But in the following, we will not use the framework, right? We don't use the convergence of empirical mirror. So this is basic for motivation. Okay, so there's a equivalent characterization of so this is a classical result. So mu n, so this mu n converges to Dirac rho t in law. So A is equivalent to say the following: the K marginal converge weakly to rho to K. What is the K marginal, right? So K is bigger than 2. So K marginal is the following, right? First, this is a particle system. So we have rho n. So rho n is a joint distribution. Joint law, right? Joint law of the particle system, right? Of course, it depends on T. So we take the marginal. So you can think this as, we just choose K particles. And if we see the joint distribution of those K particles, right? So this is the weak convergence of this is probability mirror. So this is probability mirror, right? I will tell more like when I'm there, but this is basically propagation of chaos. So this is
Thank you.
basically propagation of chaos. So in the end, right, you get asymptotic independence, right? You get IID. Right? Okay, so I will explain more when we go to the framework, right? So this is basically the motivation. So as n goes to infinity, the empirical measure of IPS will converge to the as mean field dynamics. Okay.
Okay, thank you.
Yeah. So I will go on.
Okay.
Okay. So I will go back to that in 2 minutes. Okay. So I will be quick on the motion part because this is PD seminar. So many people maybe not don't working on this, but okay. So there are many models on particle system. Right? So maybe I should say this, right? So if I just consider Newton dynamics, this I will know. So you can just like gravitational force, right, in plasma, in cosmological, right, cosmological dose, right. So for in this case, right, so xi can means right galaxy, galaxy can mean a galaxy, right. So it's a very large scale. It's like our galaxy can be as one particle, right? So it's a large scale cosmological model, right? Of course, so like in plasmas, right, this can be one ion or electrons, right? So, but these are very reduced, right? So if we want to study the tokamak plasma in tokamak, this is a far reduced model, right? So it's really not realistic. This is the first step, right? But this is Newton dynamics, right? But what we focus now is not really Newton dynamics; it's first order dynamics. So if you just consider those IPS, it should mean, right? So it's called one plasma, one component plasma, right? One component plasma model. So like if we choose this K as Coulomb force, so the first order system I showed you right in last page is some people call one plasma model, or you can think this as like it's called overdamped. Like if you send so if you send in Newton dynamics, you have a parameter lambda, which indicates in a friction. You send this to be very large, so you can cover like first order system. It's called overdamped system, or maybe called a small mass limit. Yeah, I shouldn't say too much about that. Recently, there are a lot of similar interacting particles using in flocking swarming models, right? You know this. I don't know to talk too much. And also, like particle systems given by interacting particle system can also be like can also be so using to sample algorithms, sample distributions. So this is actually very popular now. So you using particles, using particle system, and you let the time goes to infinity, or maybe not goes to infinity. So evolve in technical particle system, maybe you can recover a target distribution. So this is actually very popular in our machine learning community or applied math community. Right? Okay, so there are many particle models, but usually, right, the number of particles are extremely large. Right? So in physics setting, this is like 10. This is very large, 10 to 25, and even in population model, right? If you study the speed of coronavirus, right? So the world population is in this order, or this order. So it's very large, larger number of particles. We cannot really study particle system directly. So we go to the classical idea, right? goes to Boltzmann and Maxwell, right? So deriving, so that's why we deriving macroscopic PDEs, right? So I just briefly go through the classical result, right? So classical result, there are many, right? So this is very old. So this, I guess this in kinetic Vlasov. Okay, this is a review in a way. But all those classical results require K is Lipschitz. So basically, so if you take the gradient of K, it should be bounded, and sometimes even require this is bounded. And there are a lot of development, right? You relax these assumptions. For instance, you relax K be locally Lipschitz, but everything is classical, right? Everything in the end is reduced to this, right? It's nothing in technical side. It's all based on the coupling method. Let's just me say, right? So the coupling method actually is very useful, right? So in a lot of applications, it's still the most powerful method, right? So the basic idea is this, right? So for instance, we have a interacting particle system. Let's say in the limit, we get some PDE. So rho K convolve rho equals to 0. So we just from this limited PDE, we construct IID random variable. So let's call I. So this is K convolve rho T yi dt. So I call this symmetric particle system because each one are identical, it's identical. So we just compare those two xi and yi, and those give you the difference between the particle system and the mean field dynamics. Right? It's called method. Okay, so they have some same noise, right? So that's why they are coupled, right? So this is a classical method. But for classical method, they actually works for several similar kernels. But for some very interesting kernels like the Biot-Savart kernel, right, and the person kernel, right, this is why I write this, right? This gradient floor, and this is attractive case. This is attractive case, right? So for those very interesting singular kernels, right, classical maker cannot work for these very interesting scenarios. So why I list those these numbers, right? Those kernels, because now we can treat that. Okay, yeah. So recent, just mention a little bit of recent result. I will be quick. So there are many, there are not many, right? So results give you quantitative convergence rate. But there are some discussion, right? Some result, right? But these are in numerical analysis. The setting is quite different with us, right? So those are you starting from very nice prepared data. And you can follow the Lagrange flow, let's say, of the 2D Euler. So you write the 2D Euler as a vorticity form like that. So all those results are based on, so this is coupling method. So essentially, but not essentially that, right? So if you're just using classical coupling method, you cannot do that good, right? So actually those recent results based on compactness. But since, so let's say you have a ρn, right? It's the joint distribution of the particles. You have some control for those ρn. So then you can extract some convergence subsequence, right, by the compactness argument. But if you're doing this, so no rate will be available. So because you are using compactness, right? So for different subsequence, you might converge to different limits, right? So so actually for those works, so the uniqueness part is very is, but I won't talk that a lot. So we kind of use new method we call the relative entropy, and later we combine with the interaction energy part, so we call the modulated free energy. So using those methods, you will see later shortly. So we can give convergence rate, and we can treat very singular kernels. This is the first result. I will show the basic idea of this. The idea is using relative entropy to control the growth, and we can treat the general class of kernels, right? So K can be in some negative subleft space. So like the derivative, the antiderivative of K is bounded. So and also we need the divergence part is nice. So we can using the integration by part, the entropy analysis, and law of large numbers, those techniques to give quantitative convergence rate. You will see that later. So after our result, Serfaty has a very nice result for the deterministic case. But she can treat her like Coulomb Rees type flows, very singular flows, and like ingredient flow case or conservative flow case, like both in gradient form or conservative form. So what does this mean, right? So in her case, right, K can be minus gradient phi. So phi is a very singular kernel, right? It can be Rees, right? Something very singular kernels, and also K can be some gradient, right? We do some verb, right? Do some. So this is a divergence free, right? Divergence K is free. So she can treat those two classes, and also with possible perturbation. Okay, but those are for deterministic cases. If you add noise, so those results will be destroyed. So in mean field limit problems, so actually if you have noise, you will get, so the problem becomes difficult, right? So it's actually it's counterintuitive. So most of the people thought it will be easier if you have noise. Actually, it's not true. So later, right? So later is our recent result. We add, we consider stochastic systems, but those stochastic systems can have vanishing noise. So the noise, strength of noise can go to 0 as n goes to infinity. And we can, so this basically coupled, so our previous relative entropy method and Serfaty's modulated energy method. So I will show that in the last part. Okay, so here is our framework. So from now, let's just into our framework. Maybe okay. So instead of consider a particle system, right? So particle system, so we consider the Navier equation. So we consider Navier equation. So ρn is just the joint distribution of all particles. So x1t to xnt is a joint law of all particles. Okay, this actually is a linear equation. It's a linear evolution equation. It's a forward Kolmogorov equation, usually also called master equation. And ρn, right, this is linear, but this ρn is a density function in very high dimension. This is not physical observable. So really physical observable, like temperature, pressure, those things can be computed like using marginals, right? So what is our marginal? This is K marginal. So this is K marginal. So K marginal is just, okay. So it just integrate from xk plus 1 to dxn to xn. So since those ρn are indistinguishable, so ρn is symmetric. Since those ρn are symmetric, I mean, this is well-defined notion, right? It really doesn't matter, right? So if rho n is symmetric, right, if you change the indices, it doesn't change rho n, right? It becomes invariant on the symmetric group. So rho nk actually is also symmetric. So those rho nk are physical relevant quantity. So if you want to compute temperature, pressure, for instance, you need those quantity. Okay. So if we compute, if we just integrate those equations star, right, the Navier equation, so we can get the evolution of rho n k, which will involve rho n k plus 1. This is the BBDKY. It's those names, you can solve those names in deriving all type of PDEs, right? So this basically means, right, if you, so those, if you write the evolution equation for k marginal, it will involve the next, right, the next marginal rho n k plus 1. So let's just give you one example, right? So we can write the evolution of one marginal. We can write the evolution of one marginal. So it involves two marginal. Right? The very easy idea is, so this is due to Boltzmann. So if you just assume molecule chaos, right? So which is just the independence, this is very strong, it's too strong to be true. Let's make this assumption. So if we make the independence assumption, two marginals equals to the tensor product of one marginal. So we have this limit PDE, right? This is nothing, this is just the mean field dynamics. Okay. So, but, so those assumptions are not true, right? Those assumptions are not true. Why? Because you are, so this cannot be true, right? This cannot be true because those are interacting particles. Those are only true possible. So those are possible. So if you send n goes to infinity, if you send n goes to infinity. So those are called asymptotic independence. So which is exactly right. So it's just a Keck scale, just Keck scales. So we use this notion, right? So if you have those asymptotic independence, we will have the mean field dynamics, right? So we realize the reduction, so we can derive mean field dynamics if we have these Keck scales. So as I said, right? So once, let me show you this page, right? So this is the Keck scales, right? If you fix k, right, k marginal, and you send n goes to infinity, you have asymptotic independence. So it can, this is classical result. It's very easy to show. This is independent to the empirical mirror. So of course, this empirical mirror is the projection of those rho n, right? So mu n t actually converge to rho bar. So these two are equivalent. These two are equivalent. We are using this setting. We are using this setting. And not just for strong, later you will see, we use a stronger norm. We will use relative entropy. So which will imply L1 convergence. So which will implies L1 convergence, right? So you will see in next page. But the idea is very simple, right? This is also the same for other type of derivation of PDEs, right? Nonlinear Schrödinger, for instance. Okay, so what's the Euro framework, right? The Euro framework is like this. So this is initial data, right? So we usually assume initial data is nice, right? So we can even assume the initially is IID. So which is basically IID. This is too strong, right? We can relax that, right? We can relax to this. So if initially it's IID, definitely if you look at K particles, right? So it's asymptotic independence, right? But that's too strong, right? You can relax this, right? So this is the initial assumption. So K marginals, right? Initial is K chaotic. So then we run the two dynamics. Right? So in this side, we run the particle system. We run the interacting particle system. In this side, we run the mean field dynamics. So we get the distribution and time t, we get distribution and time t as well for mean field for different dynamics. So if we can establish, right, this is our goal. So if we can establish, right, and t time, we also have Keck scales, right, then that's it, right? So this is the Euro diagram for a lot of derivation of nonlinear equations, right? The nonlinear Schrodinger or Boltzmann equation all follows this framework, right? In the following, right, in our problem, in field limit problem, we didn't use in the hierarchy, right? But this is still the same idea, right? Because this is the logic. Okay, so what is our tool, right? So we use a basic quantity which is used everywhere, relative entropy. So we scale those relative entropy by n, right? So then this becomes in order one, right? When I say this becomes in order one, it means the following. So if you have f, which is n copies of f, right? So this, and we take the scaled relative entropy. So then you just get H1F G, right? So if you scale by n, so we bring this quantity to dimension one, right? This is just intuitive explanation. Right? So once we control this, let's say if we can control, we send this to 0, right? If as n goes to infinity, this vanishing. So this quantity or this relative entropy actually can quantify chaos. So why, right? So very easy, right? So if we can control this converge to 0, right? So this is monotone. So we can control the relative entropy in k dimension by the classical TKP inequality, right? So we can have this converge to 0 as n goes to infinity, right? This is a strong convergence, right? This is not just a weak convergence, it's strong convergence. This is convergence in total variation norm. Or in L1 norm, right? So any questions? Oh, no, okay. Okay, the same idea, right? The basic idea is, okay, we just control the groups of the relative entropy, right? As long as it goes to infinity, these things, right, converge to 0, right? But of course, right, initially we should assume, right, this is vanishing and least, right? So otherwise you cannot propagating those, right? As n goes to infinity. Okay, so this is the basic idea, right? So when I visited Quoc-Hung, right, so they told me, right, similar ideas was used by Benous and Zutoni in 1990, but in different setting. But those are well known, right? Those are not new, right? These are not new. This is new in our specific problem, right? People know this for a while. Okay, let's just show you one result. These are one result. So K, so the K is in some negative subject space, and also we have divergence K is good. That you can just think this 0 or divergence K, divergence free or divergence is bounded, right? For simplicity, right? What we write here, well, you can use the entropy analysis, but for simplicity, you can just think this kernel is divergence free. So we can treat we treat the, for simplicity, let's assume theta n, right? The noise, right? The strength of noise is fixed, and you can change a little bit, right? You can change this case, or you can change to the vanishing viscosity case with some technical details. Okay, and what our result is this, right? So as long as rho bar is nice, right? Rho bar is smooth. As long as rho bar is smooth, right? So with certain assumptions, so we can propagate relative entropy, right? So we can propagate relative entropy. Right? We can propagate relative entropy by Grunwald. So this is exactly by Grunwald. And those norm, those norm and those are universal constant, right? Those are just some certain norm of K which are bounded, and M bar is just a universal constant. Okay, so what does this tells us, right? This tells us, right, for instance, if this equals to 0, so then we can show, right, that this is in the order of 1 over n, right? This is in the order of 1 over n. So in particular, this implies the k marginal and k, the limit is in the order of 1 over square root n. This actually is optimal, since this is the right order of stochastic fluctuation. Okay, in particular, right? So in this case, this result works for the Biot-Savart kernel, right? So Biot-Savart kernel to the Euler or Navier-Stokes, to the Euler or Navier-Stokes in vorticity form or T-city form. So you can write like partial T omega plus K omega gradient omega, right, equals to theta. Okay. So, so in this case, right, of course, the Biot-Savart kernel is divergence free. It's divergence free, and you can write K as a gradient. So you can write K as a gradient, right? So K actually is just a gradient of V. It's just a gradient of V. I mean, this is not a V is a matrix value, right? It's this form, right? K can really write as a gradient of V, right? So V is bounded, right? K actually satisfy all assumptions in this theory, but this theory is more general. Yeah, I don't want to say too much, but I want to give you a basic idea of this. Maybe I don't have a lot of time, so I should be quick. So the basic idea, right? So as I said before, the systemic theory is very easy, right? We just derive the evolution of relative entropy, right? So this is the form, right? Phi here, right? Phi here equals to this. Phi here equals to this. And let's assume simplicity, right? Let's assume this equals to 0. Let's assume divergence free, right? So this equals to 0. Right? What we really need to control is this term. So in the following, let's just consider Kx is the Biot-Savart law. The Biot-Savart law. So so here there are singularity, right? So there's singularity, but we can cancel this singularity by symmetrization. Not really cancel. We just make this bounded, right? So here is like a double sum. So we can change the rule of xi and xj. So in that way, right, so this is what we get. So this is what we get, right? I mean, if you assume divergence free, right, so this term goes away. And so these are bounded term, you don't need to care, right? So if it's divergence free, actually this term goes away. So for Biot-Savart kernel, this is really bounded. This is really bounded. So why, right? Because this is, so by if the limit rho bar is nice, right? So this is in this order, and K has singularity like this. Okay, so we can really show phi is bounded, right? Very easy, right? It's symmetrization used in a lot of places. But the phi is not necessarily continuous, right? We only know this phi is bounded, right? So phi, we only know this is bounded. Okay, so we want to control the growth of the relative entropy Hn, right? And this term only help, right? Basically, you can ignore this term because this is a negative term. And we want to control the relative entropy by this term. So this is really the large deviation type estimate, right? Really large deviation type estimate. So in particular, right, in our case, right, you don't need to know everything about deviation. We just note, so our choice of phi has two cancellations, right, two cancellations. So if you integrate with x or integrate with y, right, you have a cancellation. Okay. So using those, right, we can using a JSON type inequality and change those integral to first term given by relative entropy and compensated with another term. So as you know, right, this can be controlled by Grunwald, and as long as we can show this term is controlled by Cn, right, we are done, right? So to control this, right, so actually this is a rate function of a large deviation function, of certain large deviation function. But for our case, right, we just show this is bounded. This part is bounded. Okay, this is a main estimate, right? For our choice of phi, right, because phi has two cancellations, we can write this summation as the following term. So this is empirical measure, and this empirical measure is charged by IID given by rho bar. So mu(n) is charged by IID given by rho bar. Right? So anyway, we can control this term, and this term is bounded, right, universally bounded by C, right? As long as this is small enough, right? It's less than C0. Right? We can control this. So if we can control this, right, is a universal constant, right? So then this whole term is C over N, right? And what's that? Right? This is just the derivative of relative entropy, right? Then we can control everything, right, by Grunwald, right? We can prove the previous theory. But this is a very specific discussion, right? So we ignore all the details, right? Just keep on the main idea. Okay. So just a few remarks. I don't have a lot of time, so I will be quick. So if phi is continuous, right, so this is a classical result. But for our case, right, so we need phi is not continuous, right, but only bounded. Only bounded. So we need to do this explicitly, right? We should do this from the scratch. So when we do that, we use like two cancellation rules I showed you, right? But the result is basically law of large numbers for double indices. So the techniques is exactly the same. People show L2 weak law of large number. So recently, you can find a proof using martingales by Lim, Lu, and Nolan. So which use a very strong, very sharp inequality. Okay, so I have several minutes, so I will talk about the new part. So the new part, right, is basically on how to treat those type of terms. Let me just show you the result, the evolution of the relative entropy, right? So this is the computation of the time evolution of relative entropy, where you can see, so in the time evolution, right, there those terms comes out, right? So those are from the limit PDE, right? Those are from the particle system. Their divergence term of the kernel comes out, and those terms are very band, right? So why this is very band, right? So you can think, right? If k is just the log x gradient log x in 2D, right? So if you take divergence kernel, right, you get Dirac. That's some CD, right? You get Dirac. And if this is Dirac, we really don't know how to treat that, right? So we don't know how to treat that in Dirac in the integral, right? And we don't know a lot of this drawing, right? We don't really want this term. We want to cancel this term. Previously, we just using relative entropy, right? So we can treat the singularity up to, let's say d alpha, right? Alpha. So alpha is less than d minus 1. We cannot treat the person kernel, right? So in 3 dimensions, we cannot treat the inverse square law, right? So later, we realized we should combine for deterministic system. So she introduced this type of quantity, and she called this modulated energy. So it's really modulated the potential energy, right? So if to evolve, right, this quantity, right? So this quantity, right, if you see this in Fourier, right, this is kind of some weighted Fourier norm of the difference of this. It's certain Fourier norm of this probability measure, or not necessarily probability, this measure, right? This measure. And we kind of combine those two new methods, right? So our relative entropy method, right? So you don't need to do a lot of structures, right? It can be general, but we only can treat very less singular kernels, right? So like the singularity this. But Serfaty method treat like Rees, right? Rees type potentials, singular potentials, right? But you need those potentials has certain structure, right? So you can have the representation, representation result, right? So we basically combine those. So this is a new part. So new part is okay. So we introducing weights. We introducing weights in the modulated free energy. We add them together, right? So if we expand this, right, what's that, right? So first part is the Euro relative entropy, and this part, right? So Gn actually is a Gibbs mirror, and G rho n bar is the tilted Gibbs mirror, and this is tilted by rho bar. And if we expand this out, right? So what we really get is just this. So those part is the modulated potential energy, right? So you just see this, right? It's just Serfaty's. And but we take expectation, right? We take expectation. Those expectation is according to the rho n, the particle mass, right? Particle distribution. And this is very crucial because if you add different scalar there, you cannot get you cannot close the evolution of this new quantity, right? This modulated free energy. And this is the right choice, right? This is the right choice. If you do this, we get the right formula, right? So when we do the evolution, right, we get so this is the this term has a sign, right? This is a positive term, and we basically can throw this term away, and just to control the following term. And the following term is nice, right? So this is basically just our k, right? It's just our k, the kernel. And if we assume rho bar, right? Rho bar is nice, and this term is smooth, right? This term is smooth, right? You can cancel one order of singularity of k, right? Instead of divergence k, right? So here we kind of have k x minus y multiply x minus y. So here, right? So this is like 2 orders more singular than this, right? Okay. So so this is the right choice, right? So this new quantity is the right choice. We cancel the divergence term, and we can control this term, but not in a very easy way. We can control this new term. Okay. For very specific case, right? So since time is almost there, so let's just give you one example. I will show the general result later, very later, very soon. Right? So if we just choose V is the Poisson kernel, we just choose this as a Poisson kernel. So this K actually also behaves like 1 over X. Okay, so we can control this term like before, right? We can control this term by LDP, light deviation estimate. Let's use LDE, right? LDE, light deviation estimate. Okay, those are exactly the same. So we can have the explicit convergence from particle system to Patlak-Keller-Segel model. So this is our estimate. But of course, there are a lot of details I omit here. And we can do for d equals 2, right? So this choice of lemma actually is optimal. So why? Because Patlak-Keller-Segel has a very critical phenomenon, right? So it's if you have 8 pi, right? If the mass is bigger than 8 pi, you will have blow up in infinite time. So what we treat is we can show the particle approximation for any subcritical regime, right? You don't have the blow up behavior, right? When time is large. Okay. So let me just add several comments, right? So there are several points we need to treat, right, to finally get the explicit convergence rate, right? First one is our new quantity. So our new norm, right, it's not really norm, it's a quantity which quantify convergence. So first, we want to show, at least for this case, we need to show this modulated free energy really dominate, right? Is like coercive. Is effectively control the distance between rho n and the limit. Okay, so this is first. This is actually the hard part. So second, right, we need to control this from above. We need to control this from above as well, right? So we need to control this either by just the relative entropy or the free energy or the interaction energy or both. Right? So this part, at least for this case, right? For this case is relatively easy, right? For this case, because we really using the previous LDE, right, to control those terms. But to treat more general terms, right? So we need to control this, right? This might be very singular, right? So for Patlak-Keller-Segel case, right? So this term easy to show, easy to control. The hard part is here. Right? The hard part is here. Okay, but for repulsive force, and it's very singular, like Rees-Coulomb case. So we're using like Fourier to show this can be controlled by this, and that, right? So these are very delicate, and those is some parameter which depend on n, and which will vanish as n goes to infinity, right? If you combine all those, we can control En, we can have the convergence in this type or in the convergence, right? So I just give you just to show the last page, right? Last page. Okay, so in general, right? So we can have attractive part and a repulsive part, right? So repulsive part is very singular, and attractive part is acts like logarithmic, like it can be too attractive, right? Okay, so we can also treat the vanishing viscosity case. We can also treat the vanishing viscosity case. And so yeah, that's it. I will just stop here. If you have questions, I can answer.